Okay, so our next speaker is Siqi Liu.
Thanks. I'll be talking about expanders and their connection to property testing. The subtitle is just a spoiler for those who understand what these means, but we'll actually define all of these, and hopefully by the end, we'll all understand what's the connection. Okay, so expanders are a type of graphs. Usually, we say that a graph is an expander if they're well connected. So there are many different ways of defining it, but roughly speaking, we say that a graph is an expander if it takes us to remove many edges in order to disconnect the graph. Okay, so expanders appears in various areas in math, including combinatorics and functional analysis. And I personally am more familiar with its applications to computer science, so I listed a couple here, including design of fault-tolerant networks, and also design of error-correcting codes, de-randomizing algorithms, and in analysis of like mixing of Markov chain sampling algorithms. Okay, so today I will basically be giving one specific definition of expanders and generalize it to higher dimension. So it might seem a little bit unconventional, but eventually we'll see how it's connected back to graphs. So in this definition, we start off with a system of two variable linear equations over n variables, x1 through xn, over the abelian group z mod 2z. So all of the constraints are of the form xi plus xj is equal to 0. So very simple. And this system of equations could also be represented just by a graph where the vertices correspond to variables and an edge correspond to these two variables having a equation. So we can see that xi plus xj equal to 0 translate to like two endpoints of this of an edge need to be given the same assignment in the solution to this system of linear equations. So in particular, if given a system of linear equations, we construct its equation graph, and if this graph is connected, then the only true solution to this system of equations is just a constant function. So it's either all 0 or all 1. Okay, so using this, we can already define what's an expander. So the definition is the following. We say the system of equations, or equivalently the graph, is a C expander if for any G that's assignment to these set of random variables, if they violate delta fraction of the equations, then it implies that this G is delta over C close to being a constant function. Okay, so this is, by the way, this is a property of the equation. So it's saying this should hold really for all G assignments to x1 through xn.
What does delta over C close mean?
Delta, oh, right, okay, good point. Delta over C close just means like in delta, a G disagrees with some constant function on delta over C fraction of variables, right? So it's measured it this way. Okay, so property test here, basically if I'm interested in testing whether a given function is a constant function, but I don't want to read all all the coordinates, all the evaluations of the function, I just want to read, let's say, only a constant number of evaluation of this function. What I can do is I can just take a expander or a system of linear equation expander over n variables, and I just sample a random linear constraint, xi plus xj equal to 0, and I can just check whether g evaluated at xi is equal to g evaluated at xj. So if this test passed with high probability, then I should be able to deduce that this this assignment g is also close to being a constant function. So that's how the test is designed for this question about whether g is close to a constant function. Okay, so more commonly, we actually say, we actually would call a graph being an expander. So I'm here just to basically pour this notion of C expander equivalent into graphs. Here, instead of like saying that we consider a G assignment of all the variables, we just equivalently consider a partition of all the vertices into two sets, those that are assigned 1 and those that are assigned 0. So now when G violates a equation, essentially means that there is an edge that connects vertices from the two different sides of the partition. And because of that, this equivalently just translates to the fraction of edges across this thing we call a cut is equal to delta. That would imply that the smaller side of these two partitions is relatively small, in the sense it's at most delta over C. So, and also like the C is usually called a conductance for a graph, but it's probably not too important now. Okay, so we know, okay, so expanders have been studying like for decades already. So I guess just from the definition above, we can relatively straightforwardly check that a complete graph where every pair of vertex is connected by an edge is actually a one expander. But probably what's more surprising is that we know for every C that's strictly smaller than one, actually we can construct a family of expanders where the number of vertices in these family of graphs goes to infinity, but the degree of every vertex is bounded by a constant constant D, depending on C. So these would also satisfy the C expander property, and we know many such constructions like date back to like in the 80s, we have like constructions from like custom from groups with custom property T due to Lubotsky, Phillips, Sarnak, and Margulis. And later we know more like combinatorial proofs coming from graph products, like the one given by Capablo, Reingold, Viden, and Vigderson. And also we even know like random deregular graphs. So a very large family of random graphs actually are expanders. This is still to Friedman. So these all have bounded degree. So these are actually the useful ones in applications. So that's kind of usually people's goal is to construct these kind of expanders. Okay, so we talked about how to define such a thing for in like basically for graphs. Actually, this can be generalized to higher dimensional objects. And just as an example, we just go one dimension higher for now. So let's consider generalizing this notion to three lens, so system of equations with three variables. Okay, so variables are, sorry, the constraints are of the form xi plus xj plus xk, sorry, yi, yj, yk, summation is 0. Okay, so this can also be translated into a graph, a hypergraph or a complex. But a major difference here is that the variables actually correspond to edges instead of vertices. Okay, so variables are edges, and the constraints correspond to triangles or two faces. Okay, so analogous to our observation previously, here we would say that we know that if G, this graph, does not have holes, it doesn't have a, okay, there's a precise definition I'm trying to hide, but basically it doesn't have a set of like, okay, it doesn't have a set of edges such that it's not a boundary of any triangle, subset of triangle. It is not a boundary of any subset of triangles, but it also doesn't have any vertex boundary. Okay, so if G doesn't have holes, then the only solution to the system of linear equations are indicator of cuts in the graph, in this graph. So cuts are just subsets of edges where after remove it, we disconnect the complex. Okay, so maybe just real quick, I won't prove it, but real quick for intuition, you know, we can show that all cuts are actually solutions pretty simply. For example, in this, we see that these blue edges are a cut, and we see that every triangle essentially contains either two edges from the cut or no edges from the cut. And to translate this back to the linear equation case, it just means the cut indicator really satisfy all of these equations. Okay, but if we instead have a complex that has a hole, this one in the middle, these five edges form a hole really. And in this kind of graph, we can have these three edges colored blue. They are also actually a solution if we check, but they but removing them doesn't disconnect the complex. So it's not the case that all solutions are cuts in this case. But okay, but we go back and focus on the complexes without host case. Okay, so for people familiar with chain complexes, they may already observe that actually, if we consider the following cochain, where these are the set of functions over the vertices, the middle are a set of functions over edge and set of function over triangles, and the homomorphism being naturally induced by the containment relationship between the vertex and the edge and triangles. If we consider this cochain, then actually the solution to this equation, this system of equations is simply the one cocycles of this cochain. And the requirement that there is no holes really just says the one homology vanishes for this cochain. So we're saying that in this case, basically all the cocycles are also coboundaries, which coboundaries really are the indicators of cuts. Okay, but don't worry if this doesn't make sense, because I'm just going to use it abstractly. So, okay, so what's going on is now we can give the definition for this setting of a C expander. So this system is a one-dimensional C expander if for any G, that's assignment over the edges, if it violates delta fraction of these equations, then it's close to being a one coboundary. Here closeness is also evaluated by the number of coordinates where it disagreed. So, okay, naturally, this also gives us a property test. If we want to know if G is actually close to a one coboundary defined by this complex, then we can take the test of just randomly sample equation and check if evaluation sums to 0. Okay, so that's the test. Okay, so we already did dimension 1, and it's very easy to generalize to dimension C. For dimension C, we just have a larger constraint involving k+2 variables, and also we consider a complex of dimension k+1 instead of 2. Okay, now the definition is pretty much analogous. So we say that the equation or the complex is the k-dimension C expander. If actually for every assignment G over the k faces. So, okay, maybe I forgot to say that actually each of these variables correspond to a k face in this complex. So for any assignment to these variables, if it violates delta fraction of these equations, then it's also close to the k coboundary of the complex. So here's the chain complex from the 0 faces all up to the k+1 faces. And with this definition, we can design a property test for whether a function G is close to the k-dimensional coboundaries. Okay. So here now we just together see a definition of the high-dimensional expander, which more commonly is called k-dimensional coboundary expanders because of the involvement of coboundary. There are actually many different definitions of high-dimensional expanders coming from generalizing different definition of expanders. And they turns out to be non-equivalent, and each of them have their own applications. And this is a new and growing field of trying to find applications and find constructions of each of these high-dimensional expanders. And this is one of my main interests. And I think I want to end with talking about one open question. As I said, unlike expanders, 1 minute, okay, great, thanks. So unlike expanders, we actually know very little about constructions of high-dimensional expanders. So in particular, for these class of expanders, we just define, here's a summary of what we know. So first we know that complete complexes are actually k-dimensional expanders, which is, these complexes are pretty dense in the sense like every vertex in this complex is connected to n-1 other vertices. And also we know that a family of k+3 dimensional spherical buildings are also k-dimensional expanders. These are not as dense, but they're still like polynomially dense graphs. So it's kind of far from our goal of actually constructing bounded degree k-dimensional expanders. So a more recent result by Lubowski and Chapman actually gives us a bounded degree, one dimension. Oh, sorry, I wrote two here, but actually I meant one-dimensional expanders. And they come from quotients of a Brouhat-Titz building. So it's pretty good, bounded degree, but it's only in one dimension. And more recently, also by work of Golowicz and a joint work with Dickstein and Wigderson, we constructed families of k-dimensional expanders that are actually abelian Cayley complexes, and they are relatively dense in the sense like they're subpolynomial degree, but still pretty far from bounded degree. So really, I will end with this question to everyone here, like, are there elementary or not constructions of families of bounded degree k-dimensional expanders? And I'll be happy to talk about it if you're interested in this problem. Thanks.
Are there expanders over other finite groups?
Yes, I guess, okay, there are, but I guess for abelian groups, yes, that people do know for like a Z mod PZ, let's say, that people do know. And also for one dimension, people also know like for symmetric groups. Yeah, that's right.
Is there, I assume there's a spectral characterization of this.
Right.
Again, it is a suitable Laplace operator, a gap of us.
Yeah, so, okay. So in the zero dimension case, in the expander case, this have a roughly equivalent to spectral characterization. But when we go to higher dimension, actually, we could choose to generalize that spectral definition to higher dimension, but it turns out to be not equivalent to this co-boundary way of defining it that we're seeing today. So yeah, there's
So
that.
where all the examples that you listed, it's like with this specific definition.
Yeah, with this specific definition, yeah. There are the other definitions, people also know constructions. And I would say in general, this is probably the hardest to construct a type, yeah.
Is there like a topological interpretation like what you have for the Maxwell-Mincutt theorem?
A topological,
Like the co-cycle equals co-boundary, is that, can you see it that way?
yeah, you can see a co-cycle equal to co-boundary, but I think they're stronger, like that's required, but they are stronger because you need this like to be able to test it with a loss of a factor of 1 over C. That's actually stronger than just a co-boundary equal to co-cycle. And I guess maybe testing is one way of seeing it. I don't know of another good characterization of it, but there are more like local constraints that you can impose on this kind of complex, plus that cohomology vanishes. If you have these two criteria together, you can show that it's a co-boundary expansion. So there are those kind of constraints, but I'm not sure if that's topological that you're thinking about.
Like filling inequalities, or like there's this realm of like filling isoperimetry stuff that's sort of related to this, right?
But is that over Z mod 2Z though, or is it? I think
I
for
guess
Z
that's
mod 2Z there's.
Okay. Thanks, Siqi.